What if an ancient, long-vanished civilization etched a message for humanity into the very fabric of space-time? A message left at the dawn of creation, now so faint and stretched by cosmic expansion that only a true marvel of engineering could ever hope to decipher it. That marvel exists. It's a golden eye floating in the void, a time machine designed to capture the universe's first light. The James Webb Space Telescope is a gargantuan instrument, weighing a colossal 6,500 kilom, and it is protected by a sun shield that measures 14 by 21 meters, giving it a footprint roughly equivalent to a tennis court. The area of its light-collecting mirror is 6 times larger than Hubble's lens, a feature that allows it to gather a greater number of photons from more remote distances and, consequently, generate images with superior sharpness. It comes equipped with a suite of cameras and sophisticated scientific instruments, enabling it to conduct observations across the infrared spectrum. This capability is absolutely fundamental to its unique mission. Because of the universe's ongoing expansion, light from the most distant cosmic regions has been stretched to such a degree that, irrespective of its initial wavelength, it now arrives as, at a minimum, infrared light. Consequently, the sole method for observing these ancient light sources is through an infrared telescope. Moreover, infrared light possesses a much greater ability to cut through dust clouds and other visual obstructions, endowing the JWST with the extraordinary capacity to see objects that remain hidden from Hubble's view. I find myself frequently making comparisons between the JWST and Hubble, largely because the former was conceived from the outset to be Hubble's successor. Nevertheless, considering their somewhat distinct fields of observation, with Hubble focusing primarily on the visible light spectrum and the JWST operating almost exclusively in the infrared, unable to perceive certain visible light spectrums entirely, it is more precise to consider the two telescopes as complementary partners rather than direct competitors. They function in tandem, creating a formidable duo that greatly broadens our collective understanding of the cosmos. But this isn't the primary reason you are here. Your purpose is to bear witness to the profound capabilities of the James Webb Space Telescope, commencing our exploration from within our own galaxy before progressively broadening our viewpoint outward, reaching toward the very boundaries of the observable universe. You are poised to behold some truly spectacular vistas, the cosmic cliffs. Our first port of call on this cosmic voyage is a place referred to as the Cosmic Cliffs, which is also cataloged as NGC 3324. It is nestled within the Carina Nebula, situated at a distance of about 7,600 light-years from our own planet. The majestic formations you're looking at are enormous structures, standing approximately 7 light-years tall, and the scene before you represents just a tiny portion of the entire nebula. The nebula in its entirety is substantially larger, distinguished by a hollowed-out center from which powerful stellar winds, born from young stars, have swept away all the surrounding dust. What we're witnessing at this moment is the very edge of that evacuated cosmic bubble. Scientists hold a deep and profound interest in this specific area of space for a very clear reason. It offers indispensable clues about the process of star formation. The stellar winds active in this region cause dust and matter to clump together, effectively forging a stellar nursery. Yet, in spite of our long history of gazing at the stars, numerous mysteries surrounding this process continue to elude us. How precisely are stars born? What do the different phases of their development actually look like? These are questions that have proven difficult to answer. A portion of the challenge in discovering these answers is the dust itself, which is simultaneously crucial for the process and a major obstacle to observing it as it happens. It envelops the nascent stars much like a protective cocoon, shielding them from view and preventing scientists from getting a clear look at what transpires during the most pivotal moments. The James Webb Space Telescope elegantly overcomes this problem. Not only does this image present a level of detail far beyond what Hubble's image could provide, but with the aid of the JWST's onboard MIRI mid-infrared instrument, we are able to pierce through the obscuring layers of dust and reveal the secrets hidden within. Just look at how much more defined the image becomes. This will supply scientists with a wealth of data on the mechanics of star formation for many years into the future. The Southern Ring Nebula. Now that we have witnessed the birth of stars, our subsequent stop with the James Webb Space Telescope will shed more light on the end of their lives. For this, we will turn our attention a little closer to home, to NGC 3132, an object also known as the Southern Ring Nebula. The image on the left side was produced by the JWST's NIRCam, near-infrared camera, whereas the image on the right was captured using MIRI. This object is a planetary nebula, though strictly speaking, that name is something of a misnomer. While conventional nebulas are the birthplaces of stars, a planetary nebula is not a location where planets are formed. Rather, this was an unfortunate naming choice made by early astronomers who, observing the circular shapes of these nebulas, thought they bore a resemblance to planets. The name stuck, even as our scientific comprehension of the term has significantly advanced. Planetary nebulas, such as this one, come into being when dust and gas are cast off from dying stars in the final chapters of their existence. Gaining an understanding of the chemical makeup of this ejected dust is incredibly valuable, as knowing which materials are present in the universe allows us to better grasp what future generations of stars could be made of. And so, once again, the James Webb Space Telescope's ability to penetrate these layers of dust to see what is hidden inside proves to be indispensable. You can compare this to Hubble's image to fully appreciate the remarkable enhancement in detail that the JWST is capable of delivering. From this detailed data, scientists have been able to infer that the second star within this binary system has not yet detonated, meaning the creation of its own planetary nebula is an event that likely lies in the future. We can also achieve a much clearer picture of how the gravitational dance between the two stars stirs the nebula, blending the dust together into these captivating and intricate patterns. The Tarantula Nebula. Let's now push our view further beyond the confines of our own galaxy. If our goal is to witness the creation of stars, it is only logical to seek out a place like the Tarantula Nebula, located 161,000 light-years away from us. It earned its name for its visual similarity to a gigantic tarantula resting inside its silken lair. In addition to its obvious and ethereal beauty, this region holds special importance for scientists because it shares a strong resemblance to a specific epoch in the universe's history known as the Cosmic Noon. During this period, which we currently understand to have taken place approximately 1 billion years after the universe came into existence, the rate of star creation reached its absolute peak. It is widely thought that the conditions during that era would have been very similar to those we find in the Tarantula Nebula today. The James Webb Space Telescope has successfully identified stars in this region that are only just beginning to form, which presents an exceptionally fascinating period of cosmic time for detailed study. Stephan's Quintet. Let's now cast our gaze even farther outward. As our field of vision expands to these immense distances, we begin to lose the ability to resolve individual stars and instead start to perceive phenomena on a truly galactic scale. Even at this incredible scope, we can see that beautiful cosmic dances are still taking place. Stephan's quintet is a visual grouping of 5 galaxies, although it's important to note that one of them is not a true member of the group, but only appears to be close to the others from our perspective on Earth. Famously featured in the classic film It's a Wonderful Life, it is hypothesized that 4 of these galaxies are on a collision course and will eventually merge. In fact, 2 of them are already in the process of doing so. The James Webb Space Telescope provides us with a stunningly clear view of the brilliantly hot dust that is being violently ejected as these 2 central galaxies orbit one another. The gravitational forces at play here are almost unimaginably intense, and the energy being released is profound. It is a cosmic ballet that can only be truly appreciated at such enormous scales. This remarkable image was not taken in a single snapshot. Instead, it is a mosaic constructed from nearly 1,000 separate images that the James Webb Space Telescope captured and which scientists then painstakingly pieced together, giving it an extraordinary level of resolution for observing its intricate details. Webb's first deep field. Let us peer deeper still into the cosmos, to a point where even the James Webb Space Telescope is straining its capabilities to capture an image in a view known as Webb's first deep field. This image focuses on a patch of sky so incredibly small that if you were to hold a single grain of sand at arm's length, it would completely block this area from your sight in the night sky. At this vast scale, individual stars are almost completely absent from view. The vast majority of what you can observe here are not stars, which would be far too small to be detected individually, but entire galaxies. Within this image, you can clearly see the fish-eye lens effects that are produced by gravitational warping, where relatively closer cosmic objects bend the light from objects behind them, creating a distorted view of what lies beyond. We are now starting to glimpse the very edges of the known universe. Contained within this image is one of the oldest galaxies that we have ever managed to observe. It is located at such an extreme distance that the light it produced when it first formed at the dawn of the universe has only just now completed its journey to reach us. So where is it? We will have to zoom in quite a bit. Can you spot it? It is, admittedly, exceptionally small. By carefully analyzing the specific markers within the light being emitted by this tiny red galaxy, scientists can determine precisely how far it has redshifted, and from that, deduce how long its light has been traveling. Through a comparison with normal visible light from similar celestial sources, this minuscule dot was calculated to be 13.1 billion light-years away, considering that the universe is currently thought to be 13.7 billion years old. This galaxy represents one of the very earliest stellar structures we will likely ever be able to see. Now you could be feeling a bit underwhelmed by its diminutive appearance. However, there is very good reason for optimism. Let's compare this image to one taken by Hubble of the exact same region of space. It's immediately obvious that the James Webb Space Telescope's image is sharper and clearer, offering much more detail and uncovering more objects. But there's a single critical distinction between these 2 images that tells a powerful story. Hubble captured its image by staring at this patch of sky for a full 10 days, methodically gathering every single photon it could from this distant region and then compiling them into one picture. The James Webb Space Telescope, by contrast, required only half a day to take its own image. The implication here is that if the JWST was capable of producing such a rich and detailed image in just 1/20th of the time, Just imagine how much more detailed of an image it could create if it were given a comparable amount of observation time. To put it another way, this tiny little dot is almost certainly not the best that the James Webb Space Telescope can do. I trust that these images have not only given you a sense of the incredible scientific advancements made possible by the James Webb Space Telescope, but also a deeper appreciation for just how beautiful the sights of the universe truly are. Images like these have left a profound impression on me. Regrettably, we will all need to practice a bit of patience to see the full range of discoveries the JWST might have waiting for us. The James Webb Space Telescope has only recently finished its calibration phase, which allowed its instruments to cool down to their operating temperatures and ensured that every component is functioning flawlessly. There are now long queues of scientists all vying for the opportunity to use it over its anticipated lifespan of 5 to 10 years, with every single second of observation time being fiercely competed for. It is slated to investigate exoplanets for signs of hospitable atmospheres that could potentially support life, peer into nebulas to unlock the secrets of star origins, and assist us in distinguishing between an ancient galaxy much like our own and the very young galaxies that emerged shortly after the Big Bang. With an instrument as powerful as the James Webb Space Telescope at our disposal, who can possibly know what else we are on the verge of discovering? The Hubble Space Telescope. To step outside on a clear night and gaze up into the sparkling blackness of space is a truly special experience, yet it is one that doesn't fully capture the immense majesty of space and everything it holds. The effects of light pollution, distortions from our atmosphere, and the inherent limitations of our own eyesight all conspire to prevent us from thoroughly exploring the universe and unlocking all of its secrets. Fortunately, the Hubble Space Telescope, from its orbital position some 550 kilometers above the Earth, enables us to transcend these limitations and peer deeply into the cosmos, fundamentally transforming our understanding of astrophysics and shaping our knowledge of the universe, all while enchanting us with some of the most remarkable images ever captured. I'm Alex McCone, and you're watching Astrown. Today we are going to take a journey through the lens of the Hubble telescope, venturing billions of light years out into space to explore and provide context for the furthest reaches of our galaxy and far, far beyond, all the way to the most distant object ever seen by humankind. What incredible wonders will we come across along the way, and what surprises is Hubble poised to reveal in this episode? The Butterfly Nebula. Our first celestial encounter, situated 3,800 light-years from us, presents us with vast blue wings that seem to stretch out into the void. But what are we actually looking at? This is NGC 6302, more commonly known as the Butterfly Nebula, and it resides within our very own Milky Way galaxy. The Butterfly Nebula's stunning display of brilliant blue and turquoise colors is, in reality, the glowing gas that once formed the outer layer of a star. The distinctive wing-like structure shows the incredible journey this gas has taken over the last 2,200 years, now spanning a distance of more than 2 light-years. Very recent observations of the Butterfly Nebula have revealed unprecedented levels of complexity in the jets of gas and the bubbles that are erupting from the star at the nebula's core, all of which are actively contributing to the rapid changes in the wing shape that you are currently witnessing. Pismis 24, journeying farther out, to a distance of 8,000 light-years, we come across the star cluster Pismis 24. This particular cluster brings together a combination of truly remarkable phenomena. To start with, your gaze will likely be drawn to the very core of a large emission nebula which appears to rise and glow with an inner light. Next, you will certainly notice the brilliant blue stars that linger both within and around the nebula. These blue stars get their striking color from their incredibly hot temperatures, which are far hotter than our own Sun. This is a direct result of their mass, which is the primary factor that determines a star's temperature. Blue stars possess at least 3 times the mass of our Sun. These very blue stars are what give Pismis 24 its signature color and texture. The extreme ultraviolet radiation they emit causes the gas that surrounds the cluster to heat up and bubble around the stars, forming remarkable clouds and making the entire region exceptionally difficult to study. For some time, a star within the cluster known as Pismis 24R1 was thought to be the most massive star ever documented, with a mass of almost 300 solar masses. However, it is now understood to be a system of at least 3 separate stars, with each one weighing in at nearly 100 solar masses, considerably smaller than first believed, but still ranking among the largest stars ever recorded. Pismis 24 is itself a component of the diffuse nebula NGC 6357, a veritable cosmic nursery. This nebula serves as a home to a great number of protostars, which are shrouded by dark, obscuring gases. Protostars signify the very earliest stage of stellar evolution, a period during which stars gather mass from their parent molecular cloud. In addition to these protostars, there are numerous young stars that are still encased in expanding cocoons of gas, giving the entire nebula the feeling of a living, breathing organism. Palomar 12. Let's now venture even further out, traveling 60,000 light-years away, where we find Palomar 12, a globular cluster of stars suspended in the blackness of deep space, lingering on the very fringes of the Milky Way's halo. The stars in this cluster are approximately 30% younger than the other globular clusters found within the Milky Way galaxy. So, what is the secret behind their youthful appearance? They were abducted. Palomar 12 does not actually originate from the Milky Way galaxy. It comes from the Sagittarius dwarf elliptical galaxy. Roughly 1.7 billion years in the past, the Palomar 12 cluster was violently torn away from its home galaxy by powerful tidal interactions with the Milky Way. In fact, Palomar 12's original home galaxy is currently in the process of being ripped apart by our own galaxy. These immense tidal forces are generally confined to the immediate vicinity of their host galaxy, but when galaxies collide or pass in close proximity to one another, the outcomes can be quite striking, producing strange, distorted shapes or unique phenomena, as is clearly demonstrated by Palomar 12, where star clusters born in one galaxy ultimately end up residing in another. The Sombrero Galaxy. Our cosmic journey doesn't end here. Hubble empowers us to see much, much further. Let's press on with our outward expedition, now moving more rapidly between destinations, starting at a distance of 30 million light-years, where Hubble provides us with a familiar sight from a completely new perspective. This is the Sombrero Galaxy, viewed from its side. This vantage point clearly reveals the flat, disc-like shape that is characteristic of most galaxies, a perspective that we do not often get to observe. You might be wondering why this flattened configuration is the standard, given that planets, moons, and meteors all tend to be spherical. Shouldn't all galaxies follow the same pattern? The reason for the more common flat shape seen in galaxies is that, as we've noted before, the universe is in a state of constant motion. The gravitational forces generated by the supermassive black holes at the centers of galaxies cause them to rotate, and the principle of conservation of angular momentum leads to this outward, disk-like arrangement. The Sombrero Galaxy is particularly remarkable for the blindingly white core at its center and the clearly defined lanes of cosmic dust that spiral outwards, with the most prominent of these lanes lingering at the rim which gives the galaxy its iconic sombrero shape. NGC 1052 DF2, pushing onward at a distance of 65 million light-years, we can observe the broad elliptical galaxy NGC 1052 DF2. Do you see anything particularly distinctive about it? You might have noticed its unusually diffuse texture, a texture so transparent, in fact, that you can see distant galaxies right through it. This quality gives the galaxy a supernatural, almost ghostly look. But the most peculiar characteristic of all is that this galaxy is possibly missing all of its dark matter. This was the very first galaxy of its type to show such a complete absence of this mysterious substance. As for the reason why, we are not yet entirely certain. The Coma Cluster. Let's venture even farther out, this time to a distance of just over 300 million light-years from Earth. This is the Coma Cluster, an immense gathering of more than 1,000 individual galaxies, all bound together by the force of gravity. This cluster also happens to be one of the very first locations where we uncovered indications of the existence of dark matter. In the image you are looking at right now, you can see thousands of intra-cluster globular clusters. These are spherical collections of stars that are not gravitationally tied to any single galaxy, but are instead bound to the Coma Cluster as a whole. Icarus, Max J1149 lensed star 1. While this may already seem incredibly far, we can journey even farther. Over 9 billion light-years away lies Max J1149 lensed star 1, also known by its nickname Icarus, which was once the most distant single star known to us in the entire universe. As a matter of fact, the light from Icarus takes such a long time to reach us that it appears to us today in the same state it was in when the universe was only 30% of its current age. To give you a better sense of Icarus's staggering distance, at the moment this image was taken, Icarus was at least 100 times farther away than the next nearest star, Earendel WH0137 LS. And yet we can travel even further to distances that seem to defy comprehension. Nicknamed Earendel WH0137 LS, is a star located in the Cetus cluster whose light required over 12.9 billion years to finally reach us. However, as a result of the continuous expansion of the universe, the actual distance between Earendel and us is now even greater, standing at approximately 28 billion light-years. We are simply seeing it as it existed nearly 13 billion years ago. Earendel is suspected to be between 50 and 100 times the size of our Sun, and because of its immense mass, it is anticipated to explode in a supernova within just a few million years from our observational perspective. It was nicknamed Earendel after the Old English word for morning star or rising light, but the name is actually a direct reference to J.R.R., Tolkien's character Eärendil, who sailed across the sky carrying a jewel that shone as brightly as a star. Beyond its fascinating name and impressive size, Eärendil also possesses an effective surface temperature of at least 20,000 Kelvin, which is nearly 4 times hotter than our own Sun. There is also a small chance that it could be a population 3 star, which would mean it contains almost no elements other than hydrogen and helium, and it would be substantially brighter than an average star. We are only able to see this star because of an effect known as gravitational lensing, where a massive cluster of galaxies warps the light from the star around them in just the perfect alignment, causing them to behave like a gigantic cosmic lens and allowing Hubble to see much farther than it would otherwise be able to. HD1. Things are now so unbelievably distant that even the Hubble telescope is reaching the absolute limits of its capabilities. But is there anything further out that we can possibly observe On our journey to the far corners of space, yes, there is one final object that Hubble can reveal to us, the redshift galaxy known as HD1, which stands as the earliest and most distant known object in the entire observable universe. While it may appear as little more than a faint red dot to us, HD1 is actually 13.5 billion light-years away, or at least it was at the time its light was first emitted. It is now estimated to be at a current distance of 33.4 billion light-years from us, once the expansion of the universe is factored in. Even though it lies at the very edge of our perception, it does offer some revealing details. Its extremely luminous ultraviolet emissions strongly suggest that it could be a starburst galaxy, one that is producing new stars at an unparalleled rate. It might also be home to the enormous population 3 stars that were described just a few moments ago, which are far more luminous than the stars we are typically familiar with. However, these theories, along with any others, remain purely speculative due to the minimal quantity of photons we have to work with. All we can know for certain is that something exists out there, 33.4 billion light-years away, and for the time being, that is the most distant object we can perceive. To acquire more information, and perhaps even more distant views of the universe, we will require the James Webb Space Telescope, the most powerful infrared telescope ever built. But until that day comes, let's be deeply thankful for the incredible sights Hubble has shown us and for the 33 billion light-year journey it has enabled us to take. The Kuiper Belt, and what an incredible journey it is. In the dark, frigid emptiness beyond Neptune, there lies a vast and enigmatic region where the ancient relics of our solar system's birth drift in silence through the profound darkness, perfectly preserved by the deep freeze of outer space. To arrive at this shadowy realm from Earth, we must travel beyond the rocky inner planets, flying past Mars, and then continuing past the swirling storms of Jupiter and Saturn. Even farther out, beyond the blue giants of Uranus and Neptune, we at last reach our final destination. Welcome to the Kuiper Belt, a colossal ring of icy debris that encircles our solar system, much like a frozen halo. This is not simply a random collection of distant rocks. It is a time capsule from 4.6 billion years ago, containing the untouched, primordial building blocks of our cosmic home. It is a region that hosts several dwarf planets and mysterious objects that have left a great many astronomers utterly perplexed. I'm Alex McCone, and you're watching Astram. Join me today as we embark on an exploration of the worlds that lurk in the shadows of our solar system, piecing together the clues they hold about its history, about the formation of planets, the activity of comets, and perhaps even the very origins of life itself. Long before we knew with certainty that the Kuiper Belt was real, astronomers had suspected for decades that something must exist out beyond Neptune. Everyone's favorite dwarf planet, Pluto, was once believed to be a solitary object in the far reaches of the outer solar system. But something about this picture didn't quite seem right. Its small size and its highly unusual orbit strongly suggested that Pluto was not alone, and that maybe it was just one of a whole host of yet-to-be-found distant objects. In the year 1951, astronomer Gerard Kuiper first predicted the existence of a belt composed of icy objects located just beyond the orbit of Neptune. But in the absence of telescopes powerful enough to actually detect these faint objects, the idea remained purely theoretical for many decades. That all changed in 1992, when astronomers David Jewitt and Jane Liu discovered the first confirmed Kuiper Belt object, which became known as 1992 QB1. Both Pluto and its moon Charon were discovered before 1992 QB1, Pluto in 1930 and Charon in 1978. but these bodies were only officially confirmed as KBOs after that pivotal 1992 discovery. Since that time, thousands of additional Kuiper Belt objects have been cataloged, populating this remote region far beyond the orbit of Neptune. To truly appreciate the immense scale and the precise position of the Kuiper Belt, let's imagine we are traveling in a spaceship, beginning our journey at the Sun and heading out toward the far edge of our solar system. As we make this trip, let's compare the Kuiper Belt to both the more widely known asteroid belt and the much less known Oort cloud. Asteroid belt. Starting our journey close to the Sun, we quickly zip past the rocky inner planets, Mercury, Venus, Earth, and Mars. Located between the orbits of Mars and Jupiter, we come upon the asteroid belt, which is composed of the leftover materials from the time when our planets were first forming, a thin, widely spread out ring of rocky debris. The asteroid belt is situated approximately 2.2 to 3. 2 astronomical units, AU, away from the Sun, and is about 1 astronomical unit in width. As a quick reminder, 1 astronomical unit is equal to the distance from the Sun to the Earth. The vast majority of the known asteroids are found in this particular part of our solar system, with sizes ranging from the largest asteroid, Vesta, at 525 kilometers wide, which is nearly the distance from London to Belfast, down to the smallest objects, some of which are only tens of kilometers across. However, despite occupying such an enormous volume of space, the total combined mass of all the asteroids in the entire asteroid belt is only about 3% of the mass of our Moon. Beyond the asteroid belt, we come across the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, truly colossal worlds that utterly dominate the outer solar system. Finally, as we move past Neptune's orbit at a distance of 30 AU, we arrive at our destination, an even more remote and icy frontier, the Kuiper Belt. Kuiper Belt structure. This immense expanse stretches from 30 to 50 AU and is home to a wide assortment of intriguing objects, from frozen relics of the early solar system to a number of dwarf planets, including Pluto, Haumea, Eris, Makemake, and countless other smaller celestial bodies. Much like the asteroid belt, the Kuiper Belt is filled with ancient debris left over from our early solar system. In fact, Kuiper Belt objects are widely considered to be some of the oldest surviving remnants of our solar nebula, the very cloud that originally formed the planets of our solar system. At one point in the very distant past, these scattered pieces might have had the potential to come together to form yet another planetary body. However, the powerful gravity of Neptune prevented these icy objects from coalescing and never permitted them to form into something new. Unlike the asteroid belt, which is made up primarily of rocky materials, the Kuiper Belt consists mostly of frozen methane, ammonia, and water ice, which together form a frozen, thick, donut-shaped ring of cosmic debris. The Kuiper Belt contains hundreds of thousands of large, icy bodies that are bigger than 100 kilometers across, as well as more than 1 trillion comets, not to mention even smaller debris and dust. The average distance between objects in this region is so vast it can be difficult to fully comprehend. Each of those objects is, on average, between 0.02 to 0. 1 AU apart, just imagine a distance of 10 million kilometers separating objects out here in the dim outer reaches of our solar system. These icy bodies drift in almost complete silence, preserving vital clues about the origins of planets and comets. But the story doesn't end there. That was merely the main region of the Kuiper Belt. Overlapping with the outer edge of this main region is another area of the Kuiper Belt known as the scattered disk, which extends out to nearly 1,000 AU, with some Kuiper Belt objects following orbits that take them even farther beyond that. So while the asteroid belt and the Kuiper Belt do share some commonalities, As you can now see, one is vastly more expansive and massive than the other. Oort cloud. And while we may have reached the outer limit of the Kuiper belt, there is still another massive structure that completely envelops every other object and belt I've mentioned thus far. In a recent video, I talked about the Oort cloud, the colossal structure of orbiting icy debris that surrounds our entire solar system. It is located so jaw-droppingly far away that even our most powerful telescopes are unable to catch even a faint glimpse of it. So how do these two vast structures, the Oort cloud and the Kuiper belt, differ from one another? For one thing, the Kuiper belt is thousands of times closer to the Sun than the center of the Oort cloud, which is theorized to stretch from 2,000 all the way out to 100,000 AU. Another major point of difference is that the Kuiper belt is shaped like a donut, while the Oort cloud is spherical, resembling a gigantic bubble of swarming debris. But one thing that these structures do have in common is that they are both sources of the celestial phenomena that we know and recognize as comets. The Oort cloud is the source of many long-period comets, whereas the Kuiper belt is the birthplace of some short-period comets. While the Kuiper belt today remains one of the most massive structures in our solar system, it is merely a small fraction of what it once was. Originally, in its entirety, it likely contained 7 to 10 times the mass of the Earth, but the shifting orbits of the 4 giant gas and ice planets caused most of that material to be lost to the vastness of space. What is left today is no more than about 10% of Earth's mass. Not only that, but the Kuiper belt as it exists today continues to slowly erode away as objects within it occasionally collide and break into smaller pieces. Smaller fragments are left behind in their wake, and some of the resulting dust is then blown out of the solar system by the solar wind. Sometimes these collisions or the gravitational influence of Neptune will send Kuiper belt objects onto a new trajectory towards the Sun, creating short-period comets, which are defined as having orbits of less than 200 years. Over the course of time, the Sun's radiation causes these comets to shed their material, which produces the spectacular tails that we can see from Earth. Several well-known comets originate from the Kuiper belt or its scattered disk, including Halley's Comet, with its average orbital period of 76 Earth years, or Comet Shoemaker-Levy 9, which broke apart and famously smashed into Jupiter in 1994, in what was the first ever observed collision of 2 solar system bodies. As we all know, Jupiter survived, but the impact was visible from Earth and was a truly spectacular sight to witness. You can see it for yourself if you happen to check out my video on the aftermath of this incredible collision. You may have also heard in the news recently about a near-Earth asteroid that has been named 2024 Y4. While there is a very, very small chance of this asteroid colliding with our moon, or an even smaller chance of it impacting the Earth, the short-period comets that originate from the Kuiper belt pose no immediate threat to us within the next 100 or more years. In other words, you do not need to worry about that. New Horizons mission. Despite the Kuiper belt being just a small remnant of what it once was, it still presents a nearly endless frontier of objects for us to explore. And unlike the Oort cloud, which we have not yet been able to visit, we have actually been to the Kuiper belt. While the majority of what we know about the Kuiper belt comes from observations made by ground-based telescopes and the Hubble Space Telescope, NASA's New Horizons is the only spacecraft to have ever actually traveled there. It successfully performed a flyby of the dwarf planet Pluto and the Kuiper belt object 2014 MU-69, which was later given the official name Arrokoth, meaning sky in the Native American Powhatan or Algonquian language. This flyby of Arrokoth in 2019 was the most distant flyby ever conducted in the history of space exploration, taking place 1.5 billion kilometers beyond Pluto, with the New Horizons spacecraft getting as close as about 3,500 kilometers above the surface of the object. Even among the vast swarm of mysterious objects that make up the Kuiper Belt, Arrokoth still managed to surprise the New Horizons mission team. Its bizarre shape was unlike anything we had ever witnessed before in our solar system. Arrokoth is a small, icy KBO known as a contact binary, which is composed of two distinct lobes that, at some point in the distant past, merged together into a single body. Its shape bears a resemblance to a flattened snowman, measuring just 35 kilometers long, 20 kilometers wide, and 10 kilometers thick. You might not think there's a great deal to learn from this relatively minuscule object, but what Arrokoth lacked in terms of an atmosphere and diverse geology, it more than compensated for with its unique and telling structure. The strange pancake snowman shape of this particular Kuiper Belt object provides us with crucial insights into how the building blocks of planets came together in the early solar system, and how planets themselves may have formed. Arrokoth's shape appeared to give it a counterintuitive gravity field and rotation, and several scientific papers published since the flyby have led to an almost undeniable truth about how planetesimals form, something the New Horizons team did not initially expect. Planetesimals form when smaller objects come together to create larger bodies, which may then eventually combine to form a planet. Until recently, there have been two competing theories: hierarchical accretion, which proposed that small objects would crash into each other at very high speeds until they created something bigger, and local cloud collapse, where nearby objects would slowly and gently come together because of their mutual gravitational attraction, thereby forming larger and larger bodies. And now, thanks to the Arrokoth flyby and the important research conducted on the object's geology, geophysics, composition, and formation, we can be fairly certain that the theory of local cloud collapse is the correct one. The object's remarkably smooth surface and the complete lack of fractures from stress both confirm that the cosmic snowman was formed at a very low speed. Alan Stern, a planetary scientist and the lead investigator for the New Horizons mission, stated that the evidence was so compelling, we've decisively solved a multi-decade debate about how planetesimals form. And thanks to New Horizons, we get to see the most famous of all Kuiper Belt objects, Pluto. The spacecraft performed a flyby in 2015, which allowed us to get up close and personal with it like never before and capture those absolutely stunning images. The mission gathered detailed observations of Pluto and Charon, the dwarf planet's largest moon, and was also able to collect data on Pluto's other satellites, Nix, Hydra, Kerberos, and Styx. Of course, we have all seen the breathtaking photographs of Pluto's iconic heart-shaped surface region, which is also known as Tombaugh Regio. But did you happen to know that this heart-shaped feature is actually a massive glacier? The western lobe of the heart, which has been named Sputnik Planitia after Earth's very first artificial satellite, Sputnik 1, is a vast nitrogen glacier that stretches 1,000 kilometers wide and is 4 kilometers deep, and it is undoubtedly the largest known glacier in the entire solar system. The eastern lobe of the heart gets its light coloration from nitrogen that is transported from Sputnik Planitia and then deposited as ice. Not only did we receive stunning images of Pluto, but the data returned by New Horizons forever altered how we understand our favorite dwarf planet. It revealed that Pluto is far more complex than we had ever previously thought and offered vital clues to the origin of its famous heart-shaped feature. The data initially led some to believe that Pluto's heart-shaped region could be explained by the presence of an internal water ice ocean. However, a more recent study led by astrophysicist Harry Valentine from the University of Bern has uncovered another, more likely culprit. The heart shape may have been created by a low-velocity impact that left a gigantic splatter across the surface of Pluto, thereby creating the western half of the heart shape. This impact would have come in at an oblique angle, which is to say not straight on. Imagine throwing a water balloon across dry pavement in the same manner you might skip a stone across a pond. When the balloon scrapes along the pavement, it bursts, leaving an elongated splat of water across the surface. This type of angled, low-velocity impact is quite similar to how the western lobe of Pluto's heart feature may have been formed. But it's not just Pluto that we get to see up close. The images of Pluto's moon Charon were also absolutely incredible. Can you make out the enormous equatorial tectonic belt? Its very existence suggests that a long-gone water-ice ocean once existed on Charon. So what lies ahead in our ongoing quest to understand the Kuiper Belt and, by extension, our entire solar system? New Horizons is currently expected to exit the Kuiper Belt sometime between the years 2028 and 2029, and while there is no current target set for a further flyby, it remains possible that NASA will identify another suitable target in the future. New instruments like the James Webb Space Telescope could help us to further analyze the composition of various Kuiper Belt objects, and perhaps in the distant future, a robotic mission might even allow us to land on one of these mysterious objects, or perhaps even collect a sample for a return mission all the way back to Earth. Who can say what else we will discover out there in this vast frozen frontier? As our technology continues to advance, future missions will hopefully push ever deeper into the Kuiper Belt, revealing more of its long-held secrets, one icy world at a time. The Voyager missions. In the year 1977, two remarkable pioneers embarked on what could be considered one of the most epic feats of exploration ever undertaken by humanity. Their ambitious goal was to unravel the cosmic mystery that surrounds our solar system and our own place within it. Not only did they furnish us with some of the very first and best imagery of our solar system's outer planets, but they continued to send back incredible new information about our universe from the depths of interstellar space. Some 47 years and 24 billion kilometers later, the Voyager 1 and 2 probes are far more than just instruments and circuitry. They have become a symbol of humanity at its very best. Curious, audacious, ambitious, and incredibly resilient. Voyager didn't just capture dazzling photographs of our gas giants and their many moons. It captured the hearts and minds of entire generations back here on Earth. These are the probes that have journeyed further than any other object ever made by human hands. They are true trailblazers and groundbreakers. It is their unique opportunity and their unique peril to travel far beyond the reach of humanity, to capture images of things we have never before seen so close up, nor have we seen since. As Voyager mission project scientist Edward Stone reflects, "When I look back, I realize how little we actually knew about the solar system before Voyager. We discovered things we didn't know were there to be discovered time after time." So, are you curious to see what they managed to learn? I'm Alex McCone, and you're watching Astra. And in today's Supercut, we will cover everything you might ever wish to know about the Voyager missions, from the probes themselves and their grand tour, all the way to their impending and tragic finale. It stands as one of life's small ironies that it is not new, cutting-edge technology that is most profoundly advancing our understanding at the edge of our solar system, but rather very old machines. They possess an onboard computer with less memory than the one found inside your car's key fob. To this very day, they are still utilizing 8-track magnetic tape that dates back to the 1970s, which makes them older than many of you who are watching this. This is the central conundrum of deep space exploration, where immense distances and extremely long travel times can result in technology becoming antiquated by the time it has finally reached its most ambitious targets. Of course, Voyager 1 and 2 were not originally designed to travel all the way into interstellar space. They were instead constructed for a 5-year mission with the objective of exploring Jupiter and Saturn and their larger moons, a mission that was only made possible thanks to a rare, once every 176 years planetary alignment. However, after successfully completing all of its initial objectives at both Jupiter and Saturn, the Voyager mission team decided to add flybys of Uranus and Neptune to one of the probe's list of objectives. Later, after these two were also completed, NASA officially announced the commencement of the even more ambitious Voyager interstellar mission, with the express purpose of exploring the outer limits of the Sun's sphere of influence and the space beyond. This final journey would take both of the probes off the ecliptic plane into previously unexplored parts of the solar system, such as the termination shock and the denser and hotter heliosheath, before they would finally cross the heliopause and enter interstellar space. But how did these truly incredible machines manage to achieve so much far beyond the scope of their original mission? It all comes down to that old but incredibly effective technology. NASA scientists made a number of exceptionally forward-thinking design choices that ultimately allowed the probes to far surpass their initial objectives. To state it simply, they were built differently. Here's how. Let's begin with one of the most consequential decisions of all: the fuel source. Each of the probes is equipped with a long-lasting radioisotope thermoelectric generator, or RTG, which converts the heat generated from the decaying plutonium-238 isotope into electric power. These generators were capable of producing 157 watts of electrical power at the time of takeoff, which is about enough to power a laptop and perhaps charge a mobile phone as well. This might not sound like a great deal, but it was actually more than Voyager needed. While using an RTG meant that power production was in a state of constant decline, it would have in strength every 87.7 years, it would still provide enough power to keep the essential systems on the probes running until at least the year 2025. This long-term fuel capacity was certainly no accident. You see, when the Voyagers launched back in 1977, NASA was facing a unique window of opportunity. The planets would soon be in that 1 in a 176-year alignment that had last taken place during Napoleon's first reign. This rare alignment would not only permit the Voyagers to visit both Neptune and Uranus with minimal course adjustments, but would also give the probes a gravity assist from each of the 4 outer giants they visited, thereby increasing their effective velocity far beyond what they could achieve from their own rocket propulsion alone. This idea was relatively new at the time, having only been attempted previously on NASA's Pioneer missions to Jupiter and Saturn. However, this narrow window of opportunity gave NASA a very strict deadline. There simply wasn't enough time to plan follow-up missions, and the United States Congress would not earmark enough funding for a longer expedition like the Grand Tour that NASA had first proposed. So what did the Voyager team do? They devised a whole series of clever engineering feats to optimize the probes for a potentially much longer mission, and then fervently hoped that the necessary funding would follow. Each of the Voyager probes comes equipped with 11 different scientific instruments, with most of them having built-in redundancies in the event of machine failure, which can be toggled on and off in order to conserve power. To make adjustments to their course and orientation, the probes are outfitted with gyroscopes for stabilization, referencing instruments, and a total of 16 hydrazine thrusters, which includes 8 backups. Backups, and very good backups at that, were absolutely key to the remarkable longevity of the Voyager probes. They proved to be utterly vital when Voyager 2's main thrusters ceased to function after 37 years. Its backup thrusters had to be engaged after 4 long decades of idleness. And guess what? They worked perfectly, which highlights the excellent engineering that went into their design. The Voyagers also have custom-built onboard computers, which are certainly antiquated by today's standards, but were considered cutting-edge back in 1977. The probe's wide-angle and narrow-angle lens cameras are controlled by a computer command subsystem, which has fixed programs like fault detection and correction routines. Another key to their incredible success lay within their computers. Each probe had a computer known as the Attitude and Articulation Control Subsystem, or AACS. And no, it doesn't scold the Voyagers when they get a bit sassy. Attitude in this context refers to the probe's orientations with respect to the Earth, without which their high-gain antenna would be unable to either send or receive signals from NASA's Deep Space Network. This is extremely important, as the probe's transmitters only have the wattage of a refrigerator light bulb, and at such truly immense distances, their radio signals become barely detectable whispers. To successfully communicate with the Voyager team and vice versa, the probe's antenna must be precisely facing the Earth, and the Deep Space Network must in turn know exactly where they are. Otherwise, they would be lost like a needle in a 287 billion kilometer haystack. Each Voyager spacecraft has a 7-meter antenna for real-time data transmission and an 8-track digital tape recorder, DTR, capable of buffering 536 megabits for future transmission, which is enough to store 100 photographs. While this was still a huge technological leap from the earlier Pioneer probes, which had no onboard data storage at all, it's still a tiny fraction of what the smartphone in your pocket can store today. Despite these significant limitations, the DTRs were built to last. Odetics, the company that manufactured them, claimed that their DTRs could process over 4,000 kilometers of tape without showing any visible wear and tear. They had to be able to withstand the harshest environments imaginable and undergo rigors that had never before been tested. Yet the Voyager DTRs performed without any data loss or machine failure until they were finally taken offline to conserve power. Not bad at all for machines that are 12 years older than the World Wide Web. Durability was a chief concern during the planning phase of Voyager. There are a great many unknowns in a mission of this incredible magnitude. To get to Jupiter, both of the Voyagers would have to pass directly through the asteroid belt. Scientists once believed that this particular region of space would shred apart any spacecraft that attempted to pass through it. However, Pioneers 10 and 11 had previously been able to successfully pass through the asteroid belt, which emboldened the Voyager team to repeat the stunt. Nevertheless, a failure would have meant a complete disaster before the probes had even reached their very first target. Luckily, both probes made it through the asteroid belt completely unscathed, and we now know that it is mostly empty space thanks to them. Even with all of these successes, and with the probes performing far better than their engineers could possibly have hoped for, as the two spacecraft journeyed through the vastness between the planets, there was still at least one more major hurdle to cross. What would happen to the probes in the extremely cold temperatures of interstellar space? NASA installed multiple heaters on board to keep the machinery operational. Nonetheless, as the probes' power supply waned, NASA had to begin turning off some of their heaters in order to conserve energy. When the cosmic ray detector's heater was turned off 2 years ago, its temperature plummeted by a staggering 70 degrees Celsius. Needless to say, sending a repair team 23 billion kilometers out into space isn't really an option, so everyone thought the instrument would surely break. But it continued to run smoothly. The very fact that the probes have operated so well for 45 years is a powerful testament to their incredible resilience and engineering. But with all of this technology, what exactly did they see? Let's go all the way back to the beginning and follow the path they blazed across our solar system. On the 20th of August 1977, NASA launched the Voyager 2 space probe from Cape Canaveral, Florida. Its partner in crime, Voyager 1, was launched just 2 weeks later on the 5th of September. Even though both of the probes were bound for Jupiter, Voyager 1 was set on a shorter, faster trajectory, so taking off second made perfect sense. It overtook Voyager 2 on the 15th of December 1977 and exited the asteroid belt first. Together, this dynamic duo was poised to take a dazzling parade of pictures that were absolutely revolutionary for their time. But don't just take my word for it. Let's jump right in, and you'll see for yourself. Earth and Moon. Just 13 days after its launch, Voyager 1 sent this photograph back to Earth, the very first of the tens of thousands of images it would send back over the course of the next 5 years, taken from a distance of 11.6 million kilometers from Earth. It's a truly sentimental place to begin our journey. It might remind you of the famous Earthrise photo that was taken by the Apollo 11 crew from the Moon just 8 years prior. We can clearly see our blue marble and its moon off in the distance. I don't know about you, but I find this particular photo so hauntingly beautiful, especially knowing just how far this probe has traveled and how much it has seen since that day. But we've got a very long way to go. So let's move on. Jupiter. It would be nearly 2 full years before Voyager 1 finally made its approach to its first target, Jupiter. Not bad at all, considering it's 714 million kilometers away. Voyager 1 arrived first on the 5th of March 1979. You see, it travels at a speed of 17 km/s, which is 2 km faster than Voyager 2, who, despite leaving Earth first, arrived 4 months later on the 9th of July, 1979. This is because the trajectory that Voyager 1 took allowed it to gain more speed relative to the Sun. Now, Voyager 1 was not the first spacecraft to encounter Jupiter. That distinction belongs to Pioneer 10, 7 years prior in 1972. And while the Pioneer mission certainly provided some great scientific insights, it didn't quite capture the imagination of the general public. But by sending back stunning images like this one, Voyager certainly did. This is Jupiter in all of its magnificent glory. It's almost hard to accept that these are actual photographs and not paintings or some kind of AI-generated image. If you look very closely, you can spot 2 of its many moons, Io on the left and Europa, the beige-colored one, on the right. But we'll have more on them later. Luckily for us, Voyager 1 even recorded its approach to the great gas giant. It took photos at regular intervals every 10 hours, which is equivalent to 1 Jupiter day. This means the planet is at the same point of its rotation in all of the photos. The 66 photos were then spliced together to create this time-lapse movie spanning Voyager 1's approach to Jupiter from the 6th of January to the 3rd of February 1979, covering a distance of 27 million kilometers. I personally can't decide if it is more incredible or terrifying. But let's get a closer look and see what surprises this planet is hiding. Something that immediately stunned the scientists was Jupiter's atmosphere. They had expected to see east-west and west-east winds in Jupiter's different atmospheric zones. But what really caught them by surprise was the sheer amount of turbulence, plumes, and rotational movement, which are all super clear in this image. You can immediately see just how dynamic the atmosphere of Jupiter really is. Scientists had already suspected that Jupiter's most notable characteristic, its great red spot, might be a counterclockwise, rotating formation. Not only did the data from Voyager confirm this, but it also showed a surprising number of similar phenomena in other parts of the planet's atmosphere. The white spot that you can see below the Great Red Spot is just one example of these surprise storms. As it turns out, Jupiter's atmosphere is absolutely littered with them, and we had no idea. When we think of rings, we usually think of Saturn. But thanks to data from the Pioneer missions, scientists had long suspected that the same might be true for Jupiter. The data from Voyager not only confirmed the existence of 4 Jovian rings, but it was also the first mission to ever image them. This picture, which was taken as Voyager was leaving Jupiter, highlights the rings beautifully as that glowing orange line that protrudes from the planet. Before we depart from Jupiter and continue our journey, I did promise that we would come back to its moons, Io and Europa. Possibly the single biggest shock to come from the Voyager expedition was the discovery of active volcanic activity on Jupiter's moon Io. Prior to the Voyager mission, geologists had thought that Io would be covered with large impact craters, much like our own moon. While they did find circular markings on Io's surface, they didn't appear to be from craters. The dark spots that you see here indicate the presence of volcanic hotspots and vast lava lakes. This particular photo shows a lava flow from less than 1 million years ago, which is incredibly recent in geological terms and was totally unexpected. We now know Io as the most geologically active site in the entire solar system. At the time these images were being taken, it would have been incredible to capture Io in the middle of an eruption. Just imagine expecting to see a moon that was similar to ours, and then stumbling upon a site like this. These blue explosions on the surface of Io shot material and gas 100 kilometers up into space. The volcanoes are incredibly active, going off relentlessly every few hours, which treated Voyager to several jaw-dropping photographs. The next moon out from Io is Europa, and it could not be any more different. It is an icy world. Voyager 1 was the first to show us that Europa is covered by a series of curious, scratch-like markings. Scientists suppose them to be some type of ice fracture patterns on Europa's surface. It was also the data from Voyager that first suggested there might be a swirling ocean lurking beneath the ice. Today we are aware of 95 moons orbiting Jupiter. However, prior to 1979, that number was only 13. Voyager discovered 3 new satellites, Thebe, Metis, and Adrastea, which brought the total up to 16 moons by the early 80s. Sadly, we don't have any pictures of them from 1979, though they have been imaged since that time. Saturn. The next stop on Voyager's grand tour was the planet Saturn. After 21 months of travel, Voyager 1 arrived on its approach to the ringed planet in November of 1980, followed closely by its companion 9 months later, in August of 1981. As I mentioned before, when you think of rings, you think of Saturn, so let's start there. Prior to the Voyager mission, Saturn was believed to possess just 5 major rings. However, Voyager 1 revealed to us that these rings are actually composed of hundreds of thin ringlets. This was the closest flyby that any probe had undertaken at that time, which is why we gained such great detail and new learnings. Voyager also discovered a new ring, the G ring, and it also provided key details about the F ring, which had been discovered by Pioneer 2 just 1 year prior in 1979. Voyager eist den Morten Wummy. One showed us that the F-ring is kinked and has a multi-stranded nature. It also identified two shepherd moons located within the F-ring, which were named Prometheus and Pandora. This was big news at the time because this discovery confirmed scientists' theories that shepherd moons exist around narrow rings to help keep the ring material in line. Voyager also introduced us to some rather ghostly features on Saturn's B rings. They appear scattered around the rings in this photograph and are said to resemble broad spokes in a wheel. They may seem innocent, but they actually cause quite a stir within the scientific community for a while. You see, up until the year 1980, we had thought that Saturn's rings were caused exclusively by gravitational forces. That's all well and good, except for the fact that these spokes completely fly in the face of that theory. Their existence is simply not consistent with gravitational orbital mechanics. We still don't know exactly what causes them, but the leading theory involves electrostatic repulsion, separating very small dust particles away from the main surface of the ring. Sadly, as much as the data from Voyager taught us about Saturn's rings, it also taught us that Saturn is in the process of losing its rings. Gravity is slowly pulling the rings into the planet, turning them into a kind of dusty rain of ice particles. According to NASA, this process could cause Saturn's rings to completely disappear in about 300 million years. Voyager's trip to Saturn raised so many new questions that a dedicated mission was mounted in the 90s to exclusively study the ringed planet. The Cassini probe, which launched in 1997, orbited Saturn for a total of 13 years. You can check out a video of mine on what it found right here, but we aren't quite leaving Saturn's territory yet. Voyager provided some decisive breakthroughs concerning the planet's moons. We were already aware of 14 moons, but Voyager revealed 3 more, bringing the total number at the time up to 17 moons. Let's see what we can learn from Titan and Enceladus. Pioneer 11 was the first probe to image Titan, which is Saturn's largest moon, and the data it gathered captured the interest of researchers, so Voyager was sent to follow up. It discovered that Titan had a thick, nitrogen-rich atmosphere, the first and only encounter of such an atmosphere beyond our home planet. Enceladus also turned out to be exceptionally quirky. Take a close look at this photo. Enceladus is visible out in the distance with Saturn in the foreground. Now, I know it's tricky to see, but that moon is actually erupting. Enceladus spews out 300 kilos of water vapor up to 10,000 kilometers above its surface, which is 20 times its own diameter, as it orbits around Saturn. The frequent plumes of water vapor that erupt from it leave behind a donut-shaped cloud that actually feeds one of Saturn's icy rings. This data was initially suggested by Voyager data, but it wasn't until we flew the Cassini mission out there that we were able to confirm it to be true. Further geological data and imaging showed that Enceladus's terrains are an unexpected mixture of old and new. The left side of the moon, which appears quite smooth, is the newer side, and the right side, with its densely packed impact craters, is the older side. This strongly suggests that Enceladus is a very geologically active moon, which it was not previously thought to be. Before we make our way over to the wonky world of Uranus, we have to say goodbye to Voyager 1. After its flyby of Titan and Saturn's rings, its path was bent upward, taking it out of the ecliptic plane. From this point on, the probe headed straight for interstellar space. Of course, it would be another 32 years before it would actually reach that destination. But not to worry, Voyager 2 took a slingshot maneuver around Saturn instead to propel it onward to Uranus and Neptune. These would be the first and only flybys of these planets in all of human history. Uranus. 5 years after its arrival at Saturn, NASA's Voyager 2 arrived on its approach to Uranus in January of 1986. At its closest point, the probe came within 81,500 kilometers of Uranus's cloud tops. Voyager 2 revealed a complete absence of visible cloud features in Uranus's atmosphere. Unlike both Jupiter and Saturn, Uranus displayed a serene, featureless cloud deck, which challenged the preconceptions that scientists held about the atmospheric dynamics of gas giants. The false color image on the right helps to bring out the subtle differences in the atmosphere of the polar regions, which are tilted on a 98-degree axis. But it was another different kind of tilt that truly stunned the Voyager scientists. It was previously unknown whether Uranus even had a magnetic field, but the data from Voyager showed us that not only does Uranus indeed have a magnetic field, but it is also tilted at an astonishing 59 degrees. That means its magnetic and rotational poles are not at all in the same place. Until that point, it was thought that these poles were always more or less aligned. It certainly is the case here on Earth. Our magnetic and rotational poles are only shifted by about 12 degrees. The stark deviation that was found on Uranus defied all conventional planetary magnetic field models and forced scientists to completely rethink their assumptions. One side effect of this misalignment of the poles is that as the planet spins, its magnetosphere, the space that is carved out by its magnetic field, wobbles like a poorly thrown football. Scientists still don't know how to properly model it, but it might look something like this. Voyager 2's observations unveiled more details about the already known rings of Uranus and also discovered 2 more. It is the first mission to capture images of these dark rings, like its outermost ring, which is visible in this photo. The rings are composed of fine dust particles. Voyager 2 also discovered 2 shepherd moons that are orbiting one of the newly discovered rings, similar to its findings with Saturn's F ring. Here they can be seen from a distance of 4 million kilometers in a photo taken on the 21st of January, 1986. This mission significantly increased the known count of Uranian moons. Prior to Voyager 2's visit, we only knew about 5 moons orbiting Uranus. Voyager 2 sent us the first ever images of these moons, which you'll see in just a second, but it also discovered 11 more moons, bringing the total at the time to 16 moons. Voyager's discovery provided valuable data on their new moon sizes, compositions, and orbital characteristics. Today, the number of known moons stands at 27. Okay, let's get back to Uranus's 5 original moons. They all appear to be ice rock conglomerates, very similar to the moons of Saturn. Oberon and Umbriel, which are pictured here on the 24th of January, 1986, are riddled with impact craters. They seem to have very little geological activity, judging by their old and dark surfaces. Titania, which sits between those two and is the 4th furthest from Uranus, is marked by huge fault systems and canyons, indicating some degree of geologic and probably tectonic activity at some point in its history. Ariel has the brightest and possibly the youngest surface of all the Uranian moons. This photo, which was taken from just 129,000 kilometers away, suggests that Ariel underwent a period of geological activity that led to many fault valleys and extensive flows of icy material at some point in its past. Miranda is the closest of the 5 to the planet, second only in proximity to Puck, the little rocky satellite that was discovered by Voyager in 1985, and it had the most surprising findings. Voyager flew by Miranda on the 4th of January, 1986, at a distance of just 30,000 kilometers. This small moon turned out to be a captivating puzzle of geological dynamism, one that has been shaped by a very volatile history. Voyager 2 identified traces of internal melting and sporadic upwelling of icy material, which manifested in extensive canyon-like faults that plunged to depths of up to 20 kilometers. The lunar canvas is further adorned with oval racetrack-shaped features that are etched like cosmic scratches. Voyager also saw terraced regions where a mosaic of old and young, bright and dark, and heavily and lightly cratered terrains all coexist. The chevron-like characteristic seen here suggests that Miranda's original surface was pulled apart, and the fragments were then forcibly reaggregated back together. Neptune. 3 weeks later, on the 25th of January, Voyager 2 departed from Uranus and snapped this wonderful goodbye shot from a distance of 1 million kilometers as it set off to its final planetary target, Neptune. After 3 years of travel at a speed of 54,000 km/h, Neptune finally came into view. Voyager 2 approached the furthest planet in our solar system on the 25th of August 1989, just over 12 years after it first took off from Earth. It produced the first close-up images we've ever received of the giant blue planet, passing only 5,000 kilometers above its North Pole, which was the closest of any of the flybys. Hydrogen was found to be the most common element in Neptune's atmosphere, although the high abundance of methane is what gives the planet its signature blue appearance. Voyager 2 measured extraordinary wind speeds in Neptune's atmosphere, with the equatorial winds blowing at speeds reaching almost 700 km/h. These remarkable speeds were yet another surprise and highlighted just how dynamic and ferocious Neptune's weather systems truly are. Scientists also discovered a massive storm on Neptune that was aptly named the Great Dark Spot. This turbulent storm seemed to be rotating counterclockwise, just like the Great Red Spot on Jupiter, and it exhibited winds that reached up to 2,400 km/h, the strongest ever recorded in the solar system. One NASA analyst, Ken Bollinger, commented on the findings back in 1989, saying, "Every day what you see is brand new. Nobody's ever seen it. It's just an incredible feeling." There's changes going on constantly on Neptune that happen very, very fast. Voyager 2 also imaged Neptune's rings for the very first time. Up until 1986, scientists had suspected that the planet might have rings, but couldn't be entirely certain. Intriguingly, the spacecraft identified several partial ring structures, or ring arcs, within Neptune's ring system. These arcs raise a lot of questions about the mechanisms that are responsible for their formation and stability, since they mainly consist of incomplete and dusty rings. A trip to Neptune wouldn't have been complete without a quick stopover at its largest moon, Triton. The coldest known planetary body in the entire solar system, Triton turned out to have a fractured surface, complete with erupting geysers and a pinkish nitrogen ice cap covering its southern pole. Scientists also identified dark plumes, which could indicate the possibility of ice volcanoes. Voyager 2 also discovered 6 new moons that were orbiting Neptune, including these ones. As Voyager 2 turned around to snap one last look at Neptune and Triton, it had officially completed its grand tour. Neptune's gravity then bent its path downward, out of the ecliptic plane. From this point on, it continued its voyage out into interstellar space, just as its counterpart Voyager 1 had done 9 years before. Interstellar space. Speaking of Voyager 1, let's see where it has ended up since we last checked in on it back in 1980. 1 year after Voyager 2 finished up with Neptune, Voyager 1 was already about 6 billion kilometers away. In order to conserve power for the long journey into interstellar space, the scientists were going to switch off its cameras forever. However, on the advice of the great Carl Sagan, the team decided to turn the camera around for one final picture, a look back at home and just how far we had come. And so, on the 14th of February 1990, Voyager 1 took the most remote selfie in all of history from a distance of 6 billion kilometers away. The result was the infamous pale blue dot photo. In the immortal words of Carl Sagan himself, "Look again at that dot. That's here. That's home. That's us." On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. This sentiment still rings with as much power today as it did 33 years ago. But what came next for the probes? What did the Voyager probes see and do in the vastness of interstellar space? In 1981, Voyager 1 escaped the ecliptic, which is the Earth's plane of orbit around the Sun, heading 35 degrees to the north. Voyager 2 later went under the ecliptic, heading 48 degrees to the south. However, this was barely the beginning of the Voyager's incredible journeys. To actually reach interstellar space, the probes would have to traverse the termination shock, a region in which hypersonic solar winds run into fierce resistance from the interstellar wind. Beyond the termination shock, the Voyagers would encounter the heliosheath, where the slowing solar winds pile up, becoming denser and hotter, which is then followed by the heliopause, the final boundary between our heliosphere and interstellar space. But in spite of what you may think, the start of the interstellar medium doesn't actually mark the end of our solar system. Indeed, it will be another 300 years until Voyager 1 reaches the Oort cloud, the vast region of billions of icy planetesimals that surround our solar system like a gigantic bubble. And it will be another 30,000 years until it finally exits the cloud, leaving our solar system behind forever. When the Voyagers traveled through the heliosheath, they made an absolutely incredible discovery. Because the Sun's magnetic field spins in opposite directions on its north and south poles, this spin creates a ripple where they meet, which is called the heliospheric current sheet, sort of like the rings that are created by dropping a stone into water. However, when this sheet reaches the termination shock, it becomes compressed, as though the ripples were hitting the edge of a swimming pool. The Voyager probes discovered that after the termination shock, these stacked up ripples form what are known as magnetic bubbles. This means that the boundary of the heliosheath is not as smooth and clear-cut as scientists had once thought. Instead, it is a fluctuating and magnetically bubbly environment. This messy finding has prompted a complete revision of our model of the heliosheath. On the 25th of July, 2012, the Voyager 1 space probe became the very first man-made object to leave the Sun's heliosphere and enter interstellar space. It was traveling at an incredible speed of 540 million kilometers per year, or 3.6 AU. The distance at which Voyager 1 crossed the heliopause was about 120 AU from the Sun, which in itself was a revelation. It was previously unknown where exactly the heliopause occurred. Funnily enough, some early models had put it as close as Jupiter, while others placed it much further out. Remember, the heliopause is the boundary where the sun's solar wind is stopped by its collision with the interstellar medium, kind of like the crashing of two powerful bodies of water against each other. Solar wind is the steady stream of charged particles, such as electrons, protons, and alpha particles, that emanate from the sun's outer layer. The interstellar medium, by contrast, consists of charged particles, gases, and cosmic dust, left over from the Big Bang and other ancient supernovae. When these charged streams hit each other, they change their course and form a region of equilibrium which is called the heliopause boundary. At first, NASA wasn't entirely sure if Voyager 1 had truly crossed the heliopause and entered interstellar space, as their models had predicted. The probe's plasma wave detector found a massive increase in plasma density, 80 times what it had previously registered in the outer Helios heath, along with a significant spike in galactic cosmic rays. But something strange didn't happen that left the scientists completely baffled. After crossing the heliopause, Voyager 1 detected absolutely no change in the ambient magnetic field. Why was that so surprising? Well, theoretical models had assumed that the ambient magnetic orientation would change in a region that was dominated by the magnetic fields of other stars. But remarkably, Voyager 1 detected no discernible change in the ambient magnetism. NASA was so confused by this that they waited nearly a full year before they announced that Voyager 1 had, in fact, entered interstellar space. On the 5th of November 2018, Voyager 2, which was traveling at the slightly slower speed of 490 million km or 3.3 AU per year, joined Voyager 1 in becoming the second man-made object to enter interstellar space. The crossing also occurred at 120 AU from the Sun, and just like Voyager 1 6 years earlier, the probe detected no change in the ambient magnetic field. But something else surprised the scientists. You see, the Sun goes through 11-year solar cycles, during which its activity waxes and wanes. Voyager 2's crossing occurred at a time when the solar winds were peaking. Models had predicted that the size of the heliosphere would fluctuate with the solar cycle, which meant it should have been expanding when Voyager 2 made its crossing. Yet Voyager 2 crossed the heliopause at exactly the same distance that Voyager 1 had 6 years prior, meaning our models were wrong. Just like the magnetometer finding, this demonstrated the immense value of testing theoretical models with actual field data. We now suspect that the boundary between the heliosphere and the interstellar medium is much more twisted and filled with fluctuations than prior models had proposed. One leading idea is that our Sun emerged billions of years ago from a hot and heavily ionized region following the explosion of one or more supernova, and that this magnetic turbulence persists to this day near the heliopause. If that is so, the probes will likely encounter a different magnetic orientation as they travel further away, but their instruments will probably have been long dark by that time. After all, the probes are already starting to show their age and fail. In early May of 2022, Voyager 1's signal went strange. Imagine for a moment that you are a NASA scientist. You arrive at your computer for the day and begin looking through the Voyager 1 telemetry data. Voyager 1 sends back status updates about its various systems, letting you know whether everything is functioning normally. It now takes 22 hours for a signal to reach Earth from Voyager 1, so communication is a little slow between you and the spacecraft you're overseeing. Currently, it is more like sending letters than it is like sending texts. However, today something is wrong. The information it has sent you is complete gobbledygook. Instead of precise data explaining exactly what Voyager 1's thrusters are doing and what orientation it believes itself to be at, you get long strings of zeros, or 377s. The information simply does not make any sense. It suggests that Voyager is doing things and pointing in directions that it physically cannot be. You quickly check your computer again. Yes, you did just receive a signal from Voyager 1, so its antenna must be pointing directly towards you, the same as it always has. It cannot be pointing in the strange directions it is claiming, or you would not be getting a signal at all. And not only are you receiving the signal, but it's at the exact same strength too, so it has definitely not changed its direction. And ping. Onto your computer comes Voyager 1's latest science data. Strangely enough, this is all completely normal. While over the years Voyager 1 has had to turn off 5 of its 11 pieces of scientific equipment, and a further 2 have stopped working due to general degradation, the remaining 4 have continued to take readings about the interstellar medium, magnetic fields, and cosmic rays. Nothing in this data is garbled in any way. You check the other systems. Voyager 1's power supplies are a little bit low, but that's to be expected. The plutonium oxide that fills its 3 generators has a half-life of 87 years, but Voyager 1 has now been traveling for 45 years. It's no wonder that its efficiency has started to decline. In fact, the experts believe that Voyager 1 will not last past the year 2025. But that's still some time away. It does not explain what is happening right now. After checking its other systems, it is just one that is behaving strangely, the AACS, the Attitude Articulation and Control System. This computer is one of 3 on board Voyager 1, and remember, its job is to make sure the spacecraft's large 3-meter antenna continues to point towards Earth. This AACS has stopped sending coherent data. You lean back in your chair, puzzled. The situation is not as bad as you might have initially thought, but it is troubling. It's kind of like receiving mail from a postman who says hello to you every morning, only for some reason he starts speaking another language one day. The packages he delivers are still the same, and they've arrived at the same address. It's just the words the man speaks make no sense to you anymore. To further compound the strangeness, Voyager 1 doesn't think that anything is wrong with it at all. The spacecraft comes equipped with emergency safe mode settings that it can go into if it detects that anything is not working the way it ought to be. Essentially, these involve powering down until scientists can figure out what's wrong with it, and these have not activated. So Voyager 1 believes that all its systems are working exactly the way they should be. The data is given, the scene is set. This was the question that NASA engineers were faced with in mid-2022. A single fault like this might not seem like a big deal, but it hints at something potentially wrong with further systems, and if that is true, it might spell an end to the whole mission. Voyager 1 is by now 23.8 billion kilometers away from you. Your solution will have to be made via deduction alongside careful 22-hour each-way questions and answers with the faulty spacecraft. By evaluating the rest of the systems and finding them to be normal, you can rule out some of the more unusual explanations. No, this probably is not the work of aliens trying to mess with you, although NASA scientists were open to the idea of the Voyager probes maybe one day being picked up by alien life, as is evidenced by the golden discs installed on the probes, which are filled with messages about us for aliens to read if they ever stumbled across it. This was more of a symbolic gesture. Besides, it seems that this would be a strange way for aliens to try to communicate with us. And no, the laws of physics have not broken down. Voyager 1 has not entered a wormhole that is skewing where it thinks it is while still somehow getting the signal back to you. Given that the scientific data all appears to be providing normal readouts, it's much more likely that the problem lies with the AACS itself. For 4 long months, scientists and engineers gently prodded and examined Voyager 1, testing theory after theory and trying to come up with a solution that fixes things without causing any further damage. In the process, they could switch over to a backup system. It would not be the first time they'd started using a new computer on Voyager 1 after the old one stopped working. Voyager 1 is built with multiple redundancies. This isn't even the first AACS computer that's been used. A previous one became defective a while ago. They also contemplated just leaving things be. After all, the science data is still coming in. Would it be the end of the world if Voyager 1 simply carried on speaking these garbled messages? Perhaps this could just be the new normal, except it implies that a deeper problem is being overlooked. Can you figure out what was going wrong? If you can, perhaps NASA should look into hiring you. It turns out that in the intense radiation-filled environment of interstellar space, something had made Voyager decide to start using that older, broken AACS computer to send data back to Earth. Because of the faults in this particular computer, the data had become corrupted, which resulted in the strange numbers. So actually, in this case, the fix was easy. All NASA had to do to fix it was to simply ask Voyager to start using the right computer again. Once Voyager 1 did that, the problem was completely resolved. Well, I say easy, and I say resolved. It still took a couple of months for Voyager 1 to start behaving normally again. And even then, in November of 2023, another of Voyager's onboard computers, this time the Flight Data Subsystem, underwent a similar problem and became unable to send home usable science and engineering data. It took until June of 2024 until that problem was fully resolved. Voyager 1 is an old ship now. As it continues to travel through the vastness of interstellar space, it may encounter more and more faults. In July of 2023, a routine series of commands that were sent to Voyager 2 caused the probe to orient its antenna 2 degrees away from Earth. This seemingly small divergence was enough that, over the massive distances involved, NASA completely lost the ability to talk to Voyager 2 or hear back from the probe. It was only through sending out an interstellar shout from the Deep Space Network facility in Canberra, Australia, that a signal was able to be sent to Voyager 2, telling it to reorient itself back towards Earth. The 37 hours of waiting for the shout to arrive and for the probe to signal back that it had followed, the command must have been incredibly tense for the NASA personnel. The probe could have been lost forever. One way or another, it is truly inevitable that the Voyager probes will eventually stop transmitting back to Earth, whether it's through an error or a malfunction or simply by running out of power. The end is unavoidable, and the curtain will eventually fall on this incredible mission. But even then, the twin probes are just beginning their long cosmic journeys. In 40,000 years, Voyager 1 will likely drift towards a star in the Camelopardalis constellation, while Voyager 2 will pass 1.7 light-years from the star Ross 248. In 296,000 years, it will pass 4.3 light-years from Sirius. These small, intrepid probes will likely outlast the Earth itself as they continue their solitary wanderings across the vastness of the Milky Way. And if by some chance they do encounter intelligent life in one of the far reaches of our galaxy, they will stand as a testament to mankind's ingenuity and resilience.